Good morning. Thank you. I see a couple new pictures today. That's great. Love the pictures. We'll get started here in just a couple minutes. Wish I could make that link clickable as opposed to just having you guys having to copy and paste it, but I do not see a way to do that. So, oh well. Yeah. I don't see a way. Such is life. All right, here's that link again for those of you that just came in. All right, so class today. Oh, I feel like there was something else I needed to say first. There definitely was. Let me go look at my notes here. It is right here. Yeah. Oh, yeah. Just a reminder, today's the 10-day drop deadline. So if you have any classes that are 10-day drop classes and you're thinking about dropping them, today is the final date for that. It's not, this 17A is not a 10-day drop class, but you might have other classes that are, so just something to be aware of. Also, it also does mean that the add deadline for classes is next Monday, so just something else to be aware of. Digging the pictures, digging the video, thank you guys. Got about half of you with pictures. All right, but for Monday, I know I said not till Monday, so you guys have, the rest of you have until Monday to get a new picture up there. What should we talk about today? I've got a couple ideas, but is there anything that seems pressing to you guys? Fair. I did watch the lectures. It seemed like the lecture, if I was not mistaken, I feel like the lecture 5 got posted kind of late. Like I didn't see it up until, like I posted a discussion for you guys yesterday saying that I hadn't seen the lecture, and then like maybe an hour later it was up, or at least it was up for me. So it seemed like lecture 5 got posted a little bit late. Problem 9. Yeah, let me go. Let me see. I don't have his homework up. Just 1 second here. Sorry, I should have had that available and ready to go. Dropping the ball. 1 sec. Apologies. Canvas. Where are you? I think his homework is just, where did he put his homework? Files, I think. Yeah, files. Homework 1. Okay, let's take a look at homework 1. Okay, sure. Yeah, I remember looking at this one. I had this, yeah, I should have had this available already. All right, so let's take a look. And let me actually, let me move some stuff just to make sure that I'm still seeing the chat. Yeah, all right, cool. So here's what homework 1 is. And so we started to do one kind of like this the other day, but we didn't quite finish it. So for a problem like this, you really kind of are stuck just having to write it out. I'll make up some slightly different numbers. So let's say we're given, sorry, I just lost it there. AN plus 1 is the recursively defined sequence or second order difference equation. So some people say difference equation, some people say recursive. It means the same thing. Also, I need to mirror my video. Mirror my video so my brain needs to look backwards to me. 1 second. There we go. Okay. Sorry, one. Awesome. Great. So yeah, that looks right. So he's defined something similar to what I'll define here. Let's say it's, I'm gonna make it a little bit different. Let's say it's, I don't know. I don't want things to get too giant. So let's say it's 2an minus an minus 1. And we have some initial conditions. We'll start with a1 equal to 3 and a2 equal to 5. I'm sorry, I got those backwards. No, yeah, a1 equal to 5, a2 equal to 3. So if I'm making my table here of n and a sub n, I've got, when n is 1, a sub 1 is 5, when n is 2, a sub 2 is 3. And then when n is 3, I actually have to work to find a sub 3. So if I want to find a sub 3, I'm setting n equal to 2, right? So the subscript is what I want it to be. So then if n is 2, over here I'm going to have 2 times a sub 2 minus a sub 2 minus 1 is 1. So it's always going to be the preceding two terms. So for a sub whatever, it's going to be 2 times the previous term minus the previous term. And in this particular case, that's going to end up being, let's see, 2 times a2, so I get 2 times 3 minus 5, which is 1. So that's my a3. Now I'm going to find a4 in the same sort of way. I'm going to do 2 times, so again, for a4, I'm setting n equal to 2. Sorry, n equal to 3. So I get a sub 3 plus 1, which is a sub 4. So that means I'm going to have a sub 3 there, and a sub 3 minus 1 is 2 there. So I'm going to have 2 times a sub 3 minus a sub 2, which is going to give me, let's see, 2 times a sub 3, so I'm going to 2 times 1 minus a sub 2 is 3. So I'm going to end up with negative 1. And we keep going, right? A sub 5 is going to be 2 times the previous term, a sub 4, minus the previous term, a sub 3, which is going to be 2 times negative 1 minus a sub 3, which was 1. So negative 2 minus 1 is negative 3. And we just keep going, right? So we keep doing this the whole 10 times. And it's kind of a little bit tedious, but we totally could do it. So I'm going to erase this actually. So and we just keep going. So a sub 6 is 2 times a sub 5 minus a sub 4. A sub 5 is negative 3. A sub 4 was negative 1. And minus negative 1, so that's going to be negative 6 plus 1, which is negative 5. And then a sub 7 is going to be 2 times the previous term, which is negative 5. Sorry, I should write that. This problem's not fun, right? It's just kind of boring and tedious, but I mean, it is important to be able to kind of do this. So a sub 7 is 2 times a sub 6 minus a sub 5, which is negative 3. So I got negative 10 plus 3, which is negative 7. A sub 8 would be 2 times the previous term minus the previous term. So negative 14 plus 5 is negative 9. And then a sub 9 is going to be 2 times the previous term minus the previous term. So meaning negative 18 plus 7, which is negative 11. And finally, a sub 10 equals 2 times the previous term minus the previous term. That's going to be negative 22 plus 9 is negative 13. Now, this is the answer he's looking for, or something like this for the one he's giving you. As an aside, so something that is not asked for but is related, is you can actually kind of see or start to see an explicit pattern here, right? I know I erased the first two. So we started with a sub 1 equal to 5, a sub 2 equal to 3, and then we got 1, negative 1, negative 3, negative 5. Right? It looks like we're just getting, it looks like we're decreasing by 2 every time. So if someone asked you, you could probably make a reasonable guess that a sub n is equal to, I think it's what, 7 minus 2n, right? A sub 1 is 7 minus 2 times 1, which is 5. A sub 2 is 7 minus 2 times 2, which is 3. And each time n increases by 1, this whole quantity will decrease by 2 because we're subtracting 2n each time. So that's not something you have to do for this or in general. And usually it's actually a lot harder. I happen to maybe accidentally pick some numbers that worked out really nice. But you sometimes, if you're lucky, you can kind of see what the explicit formula for your sequences. To kind of go along with that, so I know last time we talked a little bit about trying to kind of find a formula for the sequence based on some of the terms given. So I just want to do one more example like that because I felt like there was one thing we didn't really cover. So let's say we had something like this that was, let's see here. Sure. So negative 3 over 2, comma, positive 7 over 5, negative 11 over 10, positive 15 over 17, negative 19 over 26. And I want to find the formula for the nth term of the sequence. Just to make sure again, here so everybody has it, there's the link to the attendance form. Please make sure you fill that out. All right, so just like with the previous examples for these sequences where we're trying to figure out the nth term, so I'm thinking, right, this is a sub 1, this is a sub 2, this is a sub 3, this is a sub 4, this is a sub 5. And I would like to know a formula for a sub n. And when I'm thinking about these, I'm thinking of it as kind of 2 or 3 separate pieces. 3 if there's an alternating thing, 2 if there's just a top and the bottom of my fraction. So here I see 3 separate things. I see the alternating part. So since it's alternating, I want to have negative 1 to the, I want negative 1 to the n or negative 1 to the n plus 1. And it really just depends on what I'm starting with. Since I'm starting with n equal to 1, and the first term should be negative, I want negative 1 to the n, because negative 1 to the 1 is negative 1. Whereas if I was starting with a positive term, I would want negative 1 to the n plus 1. So that negative 1 to the 1 plus 1 is negative 1 squared, which is positive 1. So I want this. And if your sequence is alternating, it's always going to be one of these two things. There are other ways of writing this, by the way. These are just the most convenient. In class yesterday, he did something like cosine of pi times n, which is also an alternating negative 1, positive 1, negative 1, positive 1, right? Because cosine of pi times 1 is negative 1, and cosine of pi times 2 is positive 1, and cosine of pi times 3 is negative 1. It just goes back and forth. So there's actually lots of ways to write alternating between 1 and negative 1. But these are the best ways. These are the most convenient, nice, easy to see. Oh yeah, obviously it's negative 1, 1, negative 1, 1, and so on. All right, the other pieces here are the numerator, or the top, which is, and again, I'm going to ignore the alternating part, right? I've dealt with that. I'll put it back in at the end. So my numerator is 3, 7, 11, 15, 19. And hopefully you guys can see that we're increasing by how much in each step. Thank you. Yeah, yeah. Fingers are great. If you're on video, you can show me your fingers. That's awesome. You can also type it in the chat. Do you have any other pictures? Okay. Oh yeah, I like your pictures, guys. Monday, I hope to see pictures for everybody. You don't have to have a picture of yourself. Just a picture of something. I like Catherine. I'm not sure if that's you or not, Catherine, but I like your horse picture. It's great. So if we're increasing by 4 each time, that means we need something like 4n. Now, here's what I typically do to figure out what I need to add or subtract. I know when n equals 1, I want it to be 3. If I plug in n equals 1 here, I'm going to get 4, so I need to subtract 1 to get 4 minus 1 equal to 3. And then that works for everything, right? If I plug in n equals 2, 8 minus 1 is 7. If I plug in n equals 3, 4 times 3 is 12. 12 minus 1 is 11. So it totally works. You can just do it for the first term. The denominator is a little bit trickier. He didn't do one like this, I don't think, but I wanted to show it to you because it's one that I typically ask my students all the time. So my denominator, I've got 2, 5, 10, 17, 26, etc. And I don't see any real clear pattern, and they kind of made that on purpose. So if I look at the differences between numbers, 2 to 5, the difference is 3, 5 to 10, the difference is 5, 10 to 17, the difference is 7, 17 to 26, the difference is 9. Now, here's something that's worth knowing, I think. If your differences are all increasing odd numbers, it means you have something squared. Or another way of thinking about this, which isn't super helpful just yet because we haven't started talking about derivatives yet, but if you look at the difference of the difference, so 3 to 5 is 2, 5 to 7 is 2, 7 to 9 is 2. If the difference of the difference is always the same number, it means you have a second power kind of thing. So I'm thinking this is something like n squared. But if I plug in 1, 1 squared is 1. If I plug in 2, 2 squared is 4. If I plug in 3, 3 squared is 9. It looks like all those numbers are exactly 1 away from these numbers. So it looks like what I actually need is n squared plus 1. If this seems a little tricky, I wouldn't worry too much about it. This is definitely not the main thrust of the class, but it is something that's mildly important. So putting these all together, I see that my sequence is looking like -1 to the n times 4n minus 1 divided by n squared plus 1. All right. So we could do more sequence examples if you guys want, but I think it's probably worth moving on to talking about limits, because that's definitely what he spent the bulk of class yesterday. And I'm sure he'll continue to talk about limits today. So I'm going to do some limit examples, but if you guys have questions or comments, feel free to jump in.
Oh, I had a question on the problem you just did.
Sure.
So when it comes to the denominator, do you think that the differences being like the same number, like that 2, 2, 2, is that something that happens often?
So this kind of thing happens if you have n to a power. So here's the thing, right? For this first one, I actually had n to a power here, right? So if you have n to the first power, all the differences will be the same. If you have n to the second power, the difference of the difference will be all the same. And if you had something like n to the third power, the difference of the difference of the difference would be the same. So however many levels of difference you have to go to get them all to be the same tells you what power you have on n.
So like counting the difference should be like a regular step in these type of problems.
It's kind of, it's often the stuff I look at in general. Like if I, especially when it's something like this where I can just see that the difference is the same each time. The place it doesn't work, so in fact, let me kind of show you another different example, just to kind of show you something. So in fact, I'm gonna write the sequence, and then we're gonna pretend like we don't know it. So this one's probably going to be a little tricky, but okay. So I'm going to make my sequence I'm going to make it n cubed minus 1 over 2 to the n. And then we're going to pretend like it's not there. We're going to figure out what it is, even though it's clearly right there. So here are the terms you would be given, right? If I plug in 1, I get 1 minus 1, which is 0, over 2 to the first, which you would just write 0, but we're trying to make it easy, so we write the whole fraction. And then if n is 2, 2 cubed is 8, 8 minus 1 is 7, over 2 squared is 4. N is 3, 3 cubed is 27 minus 1 is 26, over 2 to the third is 8. If n was 4, 4 cubed is 81, 81 minus 1 is 80, divided by 16, right? 2 to the fourth is 16. I'm going to go out to the sixth term here. Then it's 5, 5 cubed is 125, minus 1 is 124, 2 to the fifth is 32. And finally, if n were 6, 6 cubed is 216, minus 1 is 200. I feel like I made this. No, I didn't. Sorry, I feel like I'm just making sure. I feel like I did something stupid here. I did. So this term here, that's wrong. I apologize. So this was right. 1 cubed minus 1 is 0. 2 cubed minus 1 is 7. 3 cubed minus 1 is 26. 4 cubed, I accidentally did 3 to the fourth and got 81. But 4 cubed is 64 minus 1 is 63. Sorry about that. And then lastly, 6 cubed is 216 minus 1 is 215 over 64. Now, something to kind of as to say off to the side here. If someone gave you this sequence, but they reduced their fractions, that would be really cruel. Because written like this, you can totally see that the denominator is just powers of 2. But if you reduce this to like 13 over 4, and this to, I don't know, 62 over 30 over 16, or even smaller, 31 over 6, right? It's not going to be helpful to reduce those fractions. So let's say that we had this. So if I look at the denominator first, well, yes, we know it's powers of 2. We could just say it's 2 to the n. But let's pretend like somehow we didn't see that. So then if I write this terms in the denominator, well, if I start looking at the differences are 2, and then 4, and then 8, and then 16, and then 32. And we look at those differences, the differences are 2, and then 4, and then 8, and then 16, and then 32. But look at that, right? So when you have something like this, it's exponential, where it's 2 to the power of n, the differences keep repeating in the same pattern, meaning they're always increasing in the same way, no matter how many levels of difference you look at. So that's kind of the third option, right? You can either like the second option, I guess, really. So you can either have powers of n, where the differences at some level end up being constant, or you can have exponentials, where this looks like 2 to the n. And then your differences never end up being constant. They're always increasing in the same way at every level. For the numerator, so again, if I'm going to look at the differences, I'm going to write, okay, 0, 7, 26, 63, 124, 215. And then I'm going to look at the difference of the difference. 7. 26 minus 7 is 19. 63 minus 26 is math. 37, sure. 124 minus 63 is 61. 215 minus 124 is 76, 86, 91. That doesn't look helpful. So look at the differences of the differences. 7 to 19 is 12. 19 to 37 is 18. 37 to 61 is 24. 61 to 91 is 30. And although those aren't all the same, I can see that their differences are each 6. So it took me 1, 2, 3 levels of difference to get to the differences being constant. I know that means I have to have n to the third power. If this seems kind of weird, I would really, really stress, don't worry about it too much. This is something that more I think about a lot, but I don't think this will really come up all that much. Like, I don't think he's going to give you an n cubed. That's kind of extreme. But here I can see, okay, I know that it's looking something like n cubed. But if I plug in 1, I get 0. If I plug in 2, I get 7. So I have to subtract 1. So that 1 cubed minus 1 gives me 0, and 2 cubed minus 1 gives me 7, and so on and so forth. So that's how we could get back to n cubed minus 1 over 2 again.
Thank you.
You're very welcome. Yeah, happy to talk about it. This is very related to the idea of a derivative and kind of how repeated differentiation does something, but we haven't talked about derivatives yet, so it kind of doesn't make sense to make that connection quite yet. So the other thing he talked about, well, not that thing, but the main thing he talked about yesterday was limits, specifically limits of sequences. So when you talk about a limit of a sequence, you are specifically talking about what happens to the sequence as n gets infinitely large. So if we have a sequence like a sub n equal to, I don't know, I'm gonna make something simple like 1 over n squared. There's lots of different notation for this. He was writing, I don't know, I think he said something like an goes to something as n goes to infinity. So what we're really saying, what we're really asking about is what's the behavior of this sequence as n gets really, really large. And here, if n is getting really, really large, we're dividing by a really large number. So our 1 over n squared is going to do what? Get really large or get really small? Anybody? I think I heard someone say small. Yeah, it's going to get really, really, really small, like close to 0 small. And that's very, very standard. If you have a fraction where the denominator is getting larger and larger and larger, then the overall value of the quotient is going to get smaller and smaller and smaller. It's going to get closer and closer to 0. Right? If you plug in n equal to 1,000, 1 over 1,000 squared is 1 over 1,000,000, which is super duper small. And as n gets even bigger, the fraction gets really, really closer to 0. It doesn't ever get to equal 0 in this example, but it does get closer and closer to 0. But another way of writing this, which is more typical notation, is to write the limit as n goes to infinity of 1 over n squared. So what this notation says, or what it asks for, is what is this sequence doing as n gets really, really large? Or I should say, what is the sequence getting close to as n gets really, really large? And the sequence is getting close to 0. I want to stress here, we never actually get that 1 over n squared is equal to 0. It's not. It can't be. For a fraction to equal 0, the top has to equal 0. The top is always 1. It's never 0. What this notation is saying for us is that it's really just saying all of this. This means, wow, I can't spell. Got it again. This means that 1 over n squared gets really close to 0 as n gets larger and larger. That's the whole idea. So when you say a limit is equal to some value, what you're actually saying is, oh, the sequence is getting closer and closer to that value, but it might not actually ever equal that value, which is perfectly fine. So he talked about some limit rules in class, which are fine, and they're probably semi-important to know, but they're kind of rules that you use without knowing you're using them. So let me do an example or two. So let's say I want to find, and in this section, we're kind of still thinking of sequences. So we can say our sequence A sub n, let's say it's 2n squared plus 3n minus 1 over 5n squared plus 2n plus 6. And I want to know what the limit of this sequence is. So I could write out some terms. It's not going to be fun, right? A sub 1 would be 2 plus 3 minus 1 is 4 over 5 plus 2 plus 6 is something 13. A sub 2 is going to be 2 times 4 is 8 plus 6 is 14 minus 1 is 13 over 5 times 4 is 20 plus 4 plus, okay, right? It's not, we don't want to do this, right? You don't want to, I mean, it would be a little bit easier if you like plugged it into a calculator or made a table maybe. Like you could totally do this on Desmos actually. So let me, if you had to find terms of a sequence like this, actually let me show you. I think this might be worthwhile for just a second. Let me share my screen here and get up Desmos. One sec. Sorry, where'd you go? Screen sharing. There we are. Cool. Share. So if we entered that, so I'm going to use a sub n. I wonder if I can do a sub n. Let's try a sub n. Totally. So to do the sub, you do this the underscore. So a underscore n, and then move the arrow forward equals. And then I'm going to do this fraction. So I'm going to do, let's see here, 2n to the second plus 3n minus 1. Close that parentheses. Divided by, and then 5n squared plus 2n plus 6. The cool thing about that is actually we can kind of see, oh, it looks like this is getting closer and closer to, I don't know, it looks like the y values are getting close to 0.44, I don't know, 0.43, 0.4 something. We could go further out, 0.411. But you could also, if you click on this little plus symbol here, you can make a table. And so you can make, you can call these the n values and plug in like n equals 1, n equals 2, 3, 4, 5, right, so on and so forth. And then you can change this to being the an values above, I think. Let's try it. It's not as smart as I want it to be. What's the problem? Can you define in terms of each other? Okay, that's fair. Yes. Let's just try this. I want this to be that. I know I saw someone else do this just the other day, and oh, I think maybe I have to do this. Maybe I have to be smart. Nope. X. So close. Darn it. There's a way to do this, but I shouldn't spend our time just trying to. Anyway, you could totally find the table values. I mean, I could try this. Let's try this. A sub 1? No. Sorry, guys. I thought I had it. I thought it was smart. Maybe it's this. Nope, I don't got it. There's a way to do it, but I don't know how to do it. Anyway, still useful. Still kind of shows you the behavior of the sequence. So what I want to, I'm going to figure it out later though, for sure. Sorry about that. I wish I should have practiced ahead of time. Oh well. So you can get some other values. You could figure out a way to use that table. Maybe I'll make a little video later showing you how to do it once I figure it out. But I want to know what's happening as n gets really, really large. So what happens to a sub n as n goes to infinity? So the notation I would really prefer to use, because it's pretty standard, is what's the limit as n goes to infinity of this sequence? Now, he definitely talked about in class how you can just say it's going to be 2 over 5 because there's this rule about it being, if you have a rational function like this, which is just powers of your variable divided by, I should say, positive integer powers of your variable divided by positive integer powers of your variable. If the degree of the polynomial on top is the same as the degree of the polynomial on the bottom, and these are both degree 2, so they are the same, then the limit of that is just the quotient of the leading coefficients, in this case 2 and 5. Now, I feel like that's worth a little bit of extra explanation. So here's what I'm actually going to do. I think it's perfectly fine to say, yeah, we know it's 2/5, which is 0.4. But we can also do a little bit more work. You'd say, well, this is going to be the limit as n goes to infinity. I'm going to divide every term in the numerator and denominator by the same power of n to the second, or more generally, n to whatever the highest power in the denominator happens to be. So I'm going to divide everything by n squared. 2n squared divided by n squared, 3n divided by n squared, minus 1 divided by n squared, over 5n squared divided by n squared, plus 2n divided by n squared, plus 6 divided by n squared. Now, you don't have to show this work every time, or maybe any time for him, but it is worth knowing what's happening here. If I look at this, so I've got the limit as n goes to infinity of 2. Here, one of the n's cancels, I get 3 over n. Here, I've just got minus 1 over n squared. Over 5n squared over n squared is 5. 2n over n squared is 2 over n. And 6 over n squared is 6 over n squared. And now, here's where we're going to use a bunch of the limit rules and not going to use any of them. So here's the short way of doing this. You ask yourself what happens to each of those terms. What happens to 3 over n as n goes to infinity? Well, does it get bigger or does it get small?
Small?
Yeah, it goes to 0. What about 1 over n squared? It also goes to 0. All these things that are being divided by n or n squared or some higher power of n, if n is getting really, really large, these things are all going to get really, really small. So the answer here ends up being 2/5. Now, I feel like I should back up just a little bit and kind of explain this a little bit more, because he might expect you to do this at least once. And so I'm going to write that down again. So sorry. Limit n goes to infinity of 2 plus, what do we got here? 3 over n minus 1 over n squared over 5 plus 2 over n plus 6 over n squared. So there were some limit rules that he talked about in class. And the limit rules are specifically kind of rules for how you deal with things added or subtracted together, or divided together, or dividing by n to a power, or multiplying by a constant. So basically, here's our limit rules. If you have the limit as n goes to infinity of an plus or minus bn, you can break that up as the limit of an plus or minus the limit of bn. I should mention, this is only true if both of the limits exist in the first place. So all the limits have to already exist for this to work. Another rule we're going to use is that the limit as n goes to infinity of something divided by something else is equal to the limit of the top thing divided by the limit of the bottom thing. There is one exception though. We have to have that the limit of the bottom thing isn't equal to what? What would be a bad idea to have in the denominator there? 0. By the way, in case anyone came in a little bit late, here's the attendance link again. Please go fill that out. We're going to do it every class. If I forget, just remind me. And then the other thing we're going to use is, he said, well, actually two things. If you have the limit of a constant times a sequence, that's equal to the constant times the limit of the sequence. And finally, the last one, if you have the limit as n goes to infinity of 1 over n to some positive power, we already know that's going to be 0. So these are all the rules that we actually used to do this limit here. We just didn't say any of them, and that's very typical. We usually don't say any of the rules, but sometimes in these classes, they ask you to do 1 or 2 questions where you actually kind of say all the things. So if I have this limit, here's how I'm going to use all these rules. The limit of this fraction is equal to the fraction of the limits, meaning it's the limit of the top part divided by the limit of the bottom part. I feel like this pen has gotten squeakier. But then the limit of things added or subtracted together, I can break up into multiple limits added or subtracted together. So I can write the top part as the limit of 2. Oh, I forgot one of the rules. It's all right. The limit of 2 plus the limit as n goes to infinity of 3 over n minus the limit as n goes to infinity of 1 over n squared divided by the limit as n goes to infinity of 5 plus the limit as n goes to infinity of 2 over n plus the limit as n goes to infinity of 6 over n squared. So there's one more rule we have to use. So here's the thing. We have to pretend like we don't know that this limit is 0. I know that 6 over n squared is going to go to 0 because if n gets big, 6 divided by a giant number is going to be super small. But we don't have a rule for 6 over n squared. We have a rule for 1 over n squared, and we have a rule for bringing a constant multiple out. So we have to bring that constant multiple out and then apply this rule down here. So I think I'm going to run out of space, but maybe I won't. Oh, and the other rule I forgot to mention, sorry, is that the limit of a constant is just the constant. So if you have the limit as n goes to infinity of 2, well, 2 doesn't have any n's in it, so it's not changing, so it just stays as 2. Same thing for 5 down here. This is going to be 2 plus, I'm going to bring this 3 out, so it's going to be 3 times the limit as n goes to infinity of 1 over n minus, this one we actually can say is 0 because it is just 1 over n to a positive power divided by 5 plus, I'm going to bring this 2 out and say it's 2 times the limit as n goes to infinity of 1 over n. I'm going to bring this 6 out. 6 times the limit as n goes to infinity of 1 over n squared. And then, since these things are written in the right way now, it's 1 over some power of n. Oops, sorry, that part there. I can say that all those things in boxes are 0. So I end up with 2 plus 3 times 0 over 5 plus 2 times 0 plus 6 times 0, which is a lot of work to get back to 2/5. So let me sum up here. This is an example of doing a limit using all of the limit rules that we are supposed to know. But the way you should really do this every time is just by saying, like, in fact, I probably did too much work here. He probably wants you just to be like, oh, the degrees are the same, the limit's 2/5. You could do this work, but it's kind of unnecessary. I would say it's maybe not quite unnecessary. Also, I was looking back at my other side here, and I noticed that in this step here, oh no, never mind. Nope, I'm right. Never mind. I noticed something that wasn't true. Okay. Okay, we got 5 minutes. Okay, so here are a couple more limits you should be comfortable handling. The limit as n goes to infinity of 5n to the fourth minus 2n squared plus 1 over n plus n cubed plus 6n to the fourth. And I'm going to give you guys 2 more. I want you to think about these on your wall. This got really dark in here. Let me turn on the light. Let's just see clouds outside. Or the sun like went over the roof, kind of, probably is what actually happened. Let's see. So I'm going to give you guys these things. Sure. All right. So here are 3 different limits that all kind of have the same sort of way of being written. They're all limits of what we call rational functions, where both the top and the bottom are polynomials, meaning they have our variable raised to non-negative integer powers of n in this case. So, right, our powers are 4, 2, 0, 1, 3, 4, right? All those are non-negative integer numbers. So there are 3 different things that can happen when you have a limit of this style. You can have the degree on top and the degree on bottom be the same, which is definitely true in this first one, right? For this first one, the degree on top is 4. That's the highest power of n on top. And the degree on the bottom is also 4, the highest power of n. If the degrees are the same, then the limit is just the fraction or quotient that is the leading coefficient on top divided by the leading coefficient on the bottom. And the leading coefficient is always the coefficient of the term that's to the highest power. So this limit would be 5/6. That's one thing that can happen. The degree on top is equal to the degree on the bottom. Another thing that can happen is that the degrees can be different. In this limit here, the degree on top is 2, the degree on the bottom is 3. And when the degree on top is lesser, well, here's the way I think about it. For this one here, the denominator is getting bigger faster, right? If I plug in like something like n equal to 1,000, 1,000 squared is 1,000,000, so I've got like 5 million on top, plus some smaller numbers that don't really matter. But 1,000 cubed is 1,000,000 times another 1,000, which is 1,000,000,000. So I've got like 5 million divided by 7 billion. The bottom's a lot bigger, which means that fraction is going to be a lot smaller, meaning it's going to get closer and closer to 0 as n. If n was 1,000,000 squared divided by 1,000,000 cubed, you're going to have a much, much bigger denominator. So this is actually going to end up equaling 0 whenever the degree of the top is strictly smaller than the degree of the bottom. And then kind of the opposite thing happens when the degree on top is larger. So here the degree on top is larger, it's 3, and the degree on the bottom is 2. So here the numerator is getting bigger faster than the denominator is, right? Again, if I thought about plugging in like 1,000, I'm going to have 1,000 cubed, which is 1,000,000,000 over 6 times 1,000 squared, which is 6 million. And 1,000,000,000 divided by 6 million is pretty big. And it's going to get bigger and bigger and bigger as it gets larger. So here, the limit's going to be infinity. And then he talked about in class how like, so this limit isn't really a real number, right? Infinity is not a real number. So technically we say this limit doesn't exist, but then we know that it's getting infinitely large. So we can say, well, it doesn't exist, but it doesn't exist in the way that it's getting really, really large. And this happens whenever the degree on top, well, actually I'm gonna clarify this just a little bit. When the degree on top is greater than the degree on the bottom. But what I should really say is that when the degree on top is greater than the degree on the bottom, you can end up getting positive or negative infinity, right? If this was a negative 6x squared, sorry, negative 6n squared, and this is a positive 1n cubed here, if the signs are different between your leading terms or your leading coefficients, that's going to change the sign to be negative infinity. And he said this in class. If the signs of leading coefficients are the same, you're going to end up with positive infinity. If the signs of leading coefficients are opposite, you're going to end up with negative infinity. But if the degree on top is larger than the degree on the bottom, you get some sort of infinity. It just depends. Right, so if it was a positive on the bottom, you would get positive infinity. And if it was a negative right there on the bottom, you would get negative infinity. I was going to say, so we're about out of time. So here's where we're moving to, or at least what I think you'll be moving to today in class, is you're probably going to start talking about geometric sequences. A geometric sequence is a different word for something that looks like an exponential sequence. So, for example, a sub n equal to 2 to the n, and b sub n equal to 1/3 to the n. These are both examples of geometric sequences because each subsequent term is the previous term multiplied by the same ratio, which you usually call lowercase r. So, for example, here, the terms of the sequence are 2 to the 1 or 2 to the 0. We start sometimes with 2 to the 1, 2 squared, which is 4, 2 cubed, 2 to the 4th, etc. And every term you multiply by 2 to get to the next term, right? 2 times 2 is 4, times 2 is 8, times 2 is 16. And these numbers just get larger and larger and larger, right? They're going to get bigger without band. Yeah, Alejandra, you're exactly right. The thing we were doing before, over here, this is exactly like finding the horizontal asymptote. In fact, if you look back at that Desmos graph we did, the Desmos graph, the horizontal asymptote was 2/5 because the limit as n went to infinity was 2/5. So here the horizontal asymptote would be 5/6. Here the horizontal asymptote would be 0. And this one wouldn't have a horizontal asymptote because it's not going to be close to one particular number. But this one, since the degree on top is 1 larger than the degree on the bottom, it would have a slant asymptote, which I wouldn't worry about too much. The last thing I want to say though is, so this one 2 to the n gets larger and larger and larger, but this one 1/3 to the n actually gets closer and closer to 0. So if you start writing out your terms, your first term is 1/3 to the first, and then 1/3 squared is just 1/9, and 1/3 cubed is 1/27, and 1/3 to the 4th is 1/81st, and so on. They're getting closer and closer to 0. So if you have something like a sub n equal to r to the n, and your r value is between 0 and 1, then a sub n equal to r to the n is going to get closer and closer to 0 because you're just going to be multiplying a smaller number by itself repeatedly, which is going to make it smaller and smaller and smaller and smaller. So these geometric sequences, if this number, your base or your r, is between 0 and 1, you're going to end up getting that the sequence converges to or has a limit that is 0. All right, I think that's enough for today. If there are things you guys want to see, let me know. We're definitely going to be talking more about limits, so we're gonna very shortly stop. Well, not stop. We're going to switch over to talking about limits where you have limits of functions instead of sequences, and you're going to have n or x approaching a value that's not infinity, but some just regular number. So that's definitely what I'll plan on talking about on Monday. But if there are things you guys want to see or questions you have, start a discussion thread in Canvas, and I will definitely look at it. And I think that's it. Make sure you fill out the attendance, and hope you guys have a nice weekend. Oh, I'll post a quiz as well. The quiz will get posted. I'll probably make an announcement. I'll probably post it way before Monday because I think it'd be good to give you guys more time. So once it is posted, I will notify you in some way, shape, or form. You guys are welcome. Take care. Talk to you later. All right, I'll end the meeting now.